What's up, everyone? So today I'm going to show you guys a very interesting geometry problem. It's from the AIME. It's taken from 2016 AIME II, problem 5. So the problem goes like this. Triangle ABC0 has a right angle at C0. Its side lengths are pairwise relatively prime positive integers, and its perimeter is P. Let C1 be the foot of the altitude to AB, and for n greater than or equal to 2, let Cn be the foot of the altitude to Cn-2b in triangle Cn-1, Cn-2b. The sum n equals 2 to infinity of Cn-2, Cn-1 equals 6p. Find p. Well, there's clearly a lot going on, and it's hard to visualize what's going on without a diagram, so I'll draw a diagram in this corner. So the right triangle looks just about like this, and given A, B, and C, C0, and it tells us how the altitudes are drawn. So C1 is the foot of the altitude to AB. So C0, C1 will look something like this. So this is C1, and each successive altitude is drawn to Cn-2b in triangle Cn-1, Cn-2b. So if you want to draw C2, that would be taken from the segment C0b, that's the foot of the altitude, in triangle C1, C0b. So it would kind of look like this. So this would be C1, C2, this would be C2, C3, C3, C4, and so on and so forth, on to infinity. So, this would be C2, this would be C3, this would be C4, like so. So this is just the general idea of what's going on in the problem, and what they're specifically asking for is the perimeter. And they tell you that the sum of all of these dotted segments equals 6 times the perimeter of the actual triangle. And it's a good idea to name things, so I'm going to go ahead and name BC0 as A and AC0 as B. So by Pythagorean theorem, the length of AB is the square root of A squared plus B squared. And so here we can find the length of C0, C1, because we want to find the length of all of these segments. And you can find that by using the area formula for a triangle. And so there are 2 ways to find the area here. You can either multiply AC0 and BC0 and divide by 2, or multiply AB and this altitude and divide by 2. And so that gives us AB over 2 equals square root of A squared plus B squared times C0, C1 over 2. So kind of simplifying here, what we get is C0, C1 is equal to AB over the square root of A squared plus B squared. And we have a ton of similar triangles here, and we can use that to our advantage. So basically, a lot of right triangles, and so what we can do is we can name some angles. So let angle A, angle CAB, be alpha, and angle CBA, this guy, that's going to be beta. And so we can do a bit of naming here. So alpha, beta, alpha, beta, alpha, beta, alpha, beta, alpha, beta. You get the point. And so basically, if we want to find the length of C1, C2, we can use some trig in this triangle here. So in triangle C0, C1, C2, so C0, C1, C2, we have C1, C2 over C0, C1 is equal to sine of alpha. And it kind of becomes a trend here. So C2, C3 over C1, C2. So in triangle C1, C2, C3, C2, C3, this segment, over C1, C2, which is this segment, that also equals sine of alpha, because the angle opposing C2, C3 is alpha, as is C1, C2 here. And it's like that in every single triangle. And so we can just say generally, like Cn-1, Cn-2 over Cn-1 equals sine of alpha. So what does this tell us? Basically, it tells us a way to find each successive C segment using the value of the previous one. So, and since it's a constant, since it's sine alpha, we have ourselves a geometric series. So with our value of sine of alpha, which is A over square root of A squared plus B squared, So sine of alpha equals a over root of a squared plus b squared. If you guys don't get what I mean, I'll write out like a couple terms. So like, for example, we have c0, c1 equals ab over root of a squared plus b squared. But c1 and c2, using our little formula, would give us a squared b over a squared plus b squared. And then the next successive one, so c2, c3 would be a cubed b over a squared plus b squared to the 3 halves, and so on. So basically, we have ourselves, to find this sum, it's just a geometric sum. So we can use the formula for the sum of an infinite geometric series, which is the first term, which I'm going to call a naught, over 1 minus the common ratio. So our a naught here is ab over root of a squared plus b squared. And 1 minus our ratio would be 1 minus sine of alpha. So you'd have 1, so the square root of a squared plus b squared, minus the a, all over root of a squared plus b squared. So obviously this is kind of messy. You have some cancellations here. So that gives us ab over root of a squared plus b squared minus a. This is going to become an important part later on because this is the value of our sum. So I'm just going to erase a bit of this so we can get going here. So I'll just keep the bottom part maybe. Okay, so now we have an equation that relates 6p and this sum, and then we know that we can find p as the perimeter of the triangle. So I'm going to write out these two equations. So we kind of have a system here. A plus b plus root of a squared plus b squared equals p. That's how p is defined. So if you have these three values and sum them up, you get p. That is pretty self-explanatory. And the second part was all that math we just bashed out. So ab over root of a squared plus b squared minus a equals 6p. So one convenient thing we can do here is we can multiply both sides of this equation by 6. So multiply this by 6, multiply this by 6. And bringing this over here, what we have is, we have 6a plus 6b plus 6 root a squared plus b squared equals 6p, and then we have this equation. So we can equate these two. So you can just equate this and this. So that gives us this stuff equals ab over root of a squared plus b squared minus a. So when you bring this over here, you have ab equals the product. I'll leave this in its factored form. So you have a squared plus b squared minus a, and then multiply that by 6, obviously. I'm bringing this 6 out here. And then a plus b plus root of a squared plus b squared. So one of the things that popped out of me while I was doing this solution was that you have this minus this, and it just so happens that you have this minus this. Convenient, right? So now we have a difference of squares. So that makes things a bit easier for us. So now you have ab equals 6 times root of a squared plus b squared minus a times the root of a squared plus b squared plus a. And then you add 6 times b times this product. So 6b root a squared plus b squared minus 6ba, so basically 6ab. So if you bring this over here, you have 7ab equals, and this stuff, basically, so it's square root of a squared plus b squared whole squared, which is just the stuff on the inside, a squared plus b squared, and then a squared is, well, a squared, right? So that cancels, because you have a squared plus b squared minus a squared. So that leaves just b squared. So all of this stuff here is b squared. So you have 6b squared plus 6b root a squared plus b squared. Now that's nice. I'm just gonna erase the bottom stuff here, all over geometric sum derivation. And so now, dividing everything by b, you get this. 7a equals 6b plus 6 root a squared plus b squared. And so now, if you move this to the other side, we have something nice again. So you can see that if we squared this side, you'd have 36 as the coefficient here, and you'd have a b squared term. And if you do the same thing over here, you still have a 36b squared. So that 36b squared is going to cancel, right? So that's going to be nice. So if you do this out, so you get 49a squared minus 2 of times this and this, so 84ab plus 36b squared. You get 36 times a squared plus b squared. So I'm just going to do that out. 36a squared and 36b squared. All right, perfect. So these b squareds, like we expected, cancel. And what we're left with is 49a minus 84b equals 36a. So that happens by dividing all the a's, of course. And so that gives us 13a equals 84b. Now, normally we'd be in a jiffy, but the problem gives us that they're pairwise, relatively prime positive integers. And when you're given the ratio between them, you can just know that the values of a and b will be the smallest positive prime integers that satisfy this. So here you have a equals 84 and b equals 13. Because from this, like, they tell you that basically a over b equals 84 by 13. And so that's how you get a and b. And so just the last thing here, we got to find square root of a squared plus b squared, because we need that for the area, right? So that just requires a bit of calculation. So if you did 84 whole squared and added it to 13 whole squared, and then square root of the whole thing, that gives us the hypotenuse. So let me just do that real quick. So that will give us, so 84 whole squared is 7,056, and then add on 13 squared, and that would give us 7,225. And so this factors into 289 times 25. If you don't take my word for it, you can divide it out yourself. That's what it comes out to. And if you took the square root of all of that, square root, that would give us 17 times 5. So you have your hypotenuse. I'll just denote it C. I'll just call this C, just to be safe. 85. So all you gotta do now is add together these three side lengths. So I'll mark this off in purple real quick. And if you just erase some of this work in the middle here, we have our answer. So you gotta add 84, 13, and 85. So let me do that off to the side real quick. So 84 plus 13, and add 85, 182. So that's our answer. And that's pretty much it. I hope you enjoyed, thought you found it interesting. Yeah, have a good day. See ya.